So good afternoon, everyone. I think we should start. I still see people coming in, but the great thing of an online meeting is that people can come in very quietly. So that shouldn't stop us from getting going. It's a real pleasure to welcome you all to the resumed Heidelberg Joint Astronomy Colloquium due to circumstances, of course, at the moment on Zoom. We're all hopeful that, who knows, maybe in the next semester we can do this in person again. But nonetheless, we have an exciting schedule lineup of speakers this semester. And it is a real honor to introduce the first speaker of this semester, who has very special ties to Heidelberg, actually. So I'd like to welcome Jennifer Schober. Jennifer did her undergrads and a PhD here in Heidelberg. She got her PhD in late 2014 after working with Ralf Klessen here at ETA. After that, she moved to Nordita, where she became a Nordita postdoctoral fellow in Stockholm. She then moved on as a Marie Curie fellow at EPFL in Lausanne, where she is still today and holds an SNF Prima grant. And Jennifer is a world-leading expert in numerical and theoretical studies of magnetic fields across cosmic history, really. And I'm really excited to hear from her today on new insights on the origin and evolution of cosmic magnetic fields. And it is tradition for the joint colloquium that we welcome the speaker with an applause. And even though it is online, I would like to maintain that tradition. So I would kindly ask everybody to unmute and welcome Jennifer with a warm applause, and then we can listen to the talk. The floor is all yours, Jennifer.
Yes, well, thank you very much for this very nice introduction and the applause. I hope it's worth it. So I will today speak about the origin and evolution of cosmic magnetic fields and some very recent insights that we gained from our work. And I list here some of my main collaborators on the projects that I will present today. And I want to highlight that we are a very diverse group. So there are people working mostly in cosmology, some people who work mostly on magnetohydrodynamics in general. And also there are a few people who are experts in high energy physics and particle physics. And only this combination, I think, made these projects possible that I will present today. But let me start by setting the stage. So let me remind you briefly on the history of our universe, which I summarized here in one slide. So we're beginning here on the left-hand side with a Big Bang that is followed by a phase of rapid expansion called inflation that is absolutely needed to explain many cosmological observations. After inflation, the universe is still expanding and thereby cooling down at a much slower rate, of course. And due to this cooling, the universe went through some two major phase transitions: the electroweak phase transition, where the electromagnetic force and the weak force separated, and the QCD phase transition, during which protons and neutrons formed. These atomic particles, subatomic particles, then formed the light elements in Big Bang nucleosynthesis during the first 3 minutes of our universe. But still, the universe was fully ionized at that time, and only something like 400,000 years later, the temperature cooled down enough for recombination of atom cores and electrons. At that time, during recombination, also the CMB, the cosmic microwave background, was released that we can observe today. But besides the CMB photons, the universe was completely dark. This is why we call this phase the Dark Ages, which only ended something like 400 million years later with the formation of the first stars and galaxies. And then finally we arrive at present day, something like 13-point-something billion years later at the modern universe. Now, this is a theoretical idea, and any theoretical idea needs to be proven by either experiments or, in case of astronomy, observations. So traditionally, we can observe in astronomy photons. We can observe photons from stars up to a certain age of the universe. So for if we just search for individual stars, we can probe the universe up to, in an extreme case, of an age of 4.3 gigayears, not beyond that. If we search for, or if we probe the universe by looking at galaxies, we can reach larger distances, and we can probe the universe up to an age of 0.4 gigayears, roughly. And then with photons, we can go only as far back as to the release of the CMB, which, as I said, happened something like 400,000 years after the Big Bang. Before the release of the CMB, before recombination, the universe was a plasma, and it was an optically thick plasma, so photons could not move freely. We cannot go beyond that. We could, in principle, observe the universe at a younger age using the cosmic neutrino background, but you know, neutrinos are almost impossible to detect, so this is something very theoretical. We have not observed that, but if we could observe it, we could probe the universe up to an age of 1 second. We can also, in principle, go back further using gravitational waves to probe the very first moments of our universe. Gravitational waves have been observed, as you know, but not the primordial gravitational waves, but some locally produced gravitational waves. This will change, however, in the future with a new space-based gravitational waves observatories. And hopefully we will be able to use that in cosmology then. But also you can use intergalactic magnetic fields to probe the very beginning of the universe. This is maybe a more exotic thing to say, but it has great potential to be available to cosmology to probe the very early universe. And this is my main motivation for this talk, actually. So, so this is the outline of my talk today. I hope this serves as a nice motivation for you to follow this talk closely, because there's a potential for probing the early universe with magnetic fields. I will continue first with some observational constraints that we have for primordial magnetic fields. I will then review briefly magnetogenesis, or the origin of magnetic fields, and the evolution of magnetic fields in the early universe as we find it in most reviews. And then I will add some new twists to the story. And these new twists in the evolution of primordial magnetic fields come from a quantum effect, the so-called chiral magnetic effect, which turns out to be very important in the evolution of the primordial plasma. I will show you some simulations and some calculations on this effect, and I will also show you an application of this effect in the early universe. Okay, so what do we know about, or how can we search primordial magnetic fields? So what I show here is the large-scale structure of our universe as we see it in simulations. This is the illustrious TNG simulation, for example. So I think all of you have seen these beautiful pictures. It shows really here the dense regions of the universe where we find the galaxy clusters and galaxies. It shows these large filaments that build up the cosmic web. And all of these dense regions are quite unimportant for searching for the primordial magnetic field, because they are dynamically very active. A lot of things happen during the cosmic history. So the best place to search for primordial magnetic fields is actually cosmic void, so the intergalactic medium. This is where we can expect to find fossils of the magnetic field that was generated shortly after the Big Bang. So let's put all the constraints that we have on these void magnetic fields into one parameter plot. I'm showing here the magnetic field strength, and I'm talking about co-moving magnetic fields all the time in my talk. So magnetic fields in the co-moving unit. And I show this as a function of the magnetic correlation length, so the size of the magnetic field structures. Now, there are some regions of this parameter range that we can exclude very easily. So there's a diffusion scale if we generate magnetic fields on very small scales in the early universe, we can estimate the dissipation rate of magnetic fields, and we can say below that spatial scale there should be no magnetic fields surviving until today. So we can exclude that part of the plot. We can also exclude magnetic fields being correlated above the Hubble radius, unless there are some very exotic mechanisms to generate these magnetic fields. So we can exclude these regions easily. And then we can search for magnetic fields. So one of the most simple procedure to search for magnetic fields in space is actually Zeeman splitting. And what I show here is, in fact, one of the very first observations of a magnetic field outside of Earth. What you see here is a sunspot, and we know now sunspots have very strong magnetic fields. Now, what Hale et al. Did in the beginning of last century, they were taking spectra along this path here. And I can show you how these spectra look. So here you can see that there's a single spectral line outside of the sunspot. And when we cross the sunspot, it really splits up into a triplet. And what we see here is nothing else than the Zeeman effect. And we can use this observation to directly measure the magnetic field strength in sunspots. In the intergalactic medium, we don't see any triplets. So we can only put an upper limit here based on Zeeman splitting. What is a bit more useful is looking at the CMB, in fact, so the cosmic microwave background. There are different effects that primordial magnetic fields have on the CMB. There are direct effects. So if you have a magnetic field in the early universe, you have Lorentz force acting on the baryon fluid, and that changes the velocity, and it can also have effects on the density distribution. And there are also indirect effects. So there's additional heating from a primordial magnetic field. And there's a big theoretical construction around these different effects, and you can actually calculate how primordial magnetic fields will affect, for instance, here the temperature power spectrum of the CMB. You see here the primary spectrum, and then there at large scales, especially, there are contributions from the magnetic field. For polarization, these effects are even stronger, but it has not been observed yet. So because we cut off, our observations are cut off at a certain scale, and therefore we can only put also upper limits of the primordial magnetic field using the CMB data. Then there's a technique which is becoming more and more popular in radio astronomy, which is Faraday rotation. So that is a plasma effect that describes the rotation of a polarization plane. If you have a source down here that emits polarized radio waves, and these radio waves pass an area which is magnetized plasma, then this polarization angle will change, and we will observe a different polarization angle. This is something that is frequency dependent, this difference between θ1 and θ2. So if we observe the polarization angle at different frequencies, we can extrapolate the magnetic field strength along the line of sight. Again, something this works very well in galaxy clusters or within our galaxy, but in the intergalactic medium, we only can place upper limits. The strongest upper limit that we can place here is coming actually from Big Bang nucleosynthesis. So if you have a magnetic field in the very early universe during the first 3 minutes of the universe, that magnetic field leads to an additional magnetic pressure. And this magnetic pressure can at some point affect the cosmic expansion rate. So you will expand the universe much faster, and that means it cools down faster. In turn, that means there's less time for Big Bang nucleosynthesis to happen. And as a result, you would have a smaller amount of primordial elements. However, we can measure the primordial elements today, and therefore we can say the magnetic field should not be much stronger than something like 10⁻⁶ Gauss in the early universe. So there's one more upper limit that I would like to mention. So there's an effect of primordial magnetic fields on the primordial matter power spectrum. What you see here is the classical normal matter power spectrum produced during the early universe, during inflation. So the matter power spectrum is a function of wave number. And if we have magnetic fields, these will affect the density fluctuations depending on the field strength and also on the spectrum. We can have additional bumps in this power spectrum here. And what a PhD student, Master Sanati, in our group did recently, she was testing, she was using these modified primordial power spectra as an input in big cosmological simulations as an initial condition, and then was looking into the effects on dwarf galaxies that were forming in these simulations. So I can just show you a quick example here. Without a magnetic field, this is one of the earliest snapshots in the simulation. And this is the density field at redshift 0 without magnetic fields. If we look into a case with a primordial magnetic field, you can already see by eye that these snapshots at redshift 0 look quite different. And she was going in a bit more detail. She was studying the chemistry in her produced simulated galaxies as a function here of luminosity. And she was comparing these chemical patterns with observations in our local universe. And by that, she could really exclude very strong primordial magnetic fields because they were not consistent with what we observe today. So again, this is only an upper limit of the primordial magnetic field. So therefore, what was extremely exciting was the report of a lower limit. Because before 2010, before work published by Neronov and Fovk, also a zero magnetic field could have been just the explanation for what we are seeing. But these two people reported a lower limit based on blazar observations. Now, I briefly sketch their approach here. So they were looking at blazars. These are supermassive black holes with an accretion disk and these huge jets. In case of a blazar, we are looking directly into one of these jets. Now, these jets emit very high energy photons, TeV photons. And typically, these TeV photons have mean free paths of a few tens of megaparsec before they decay into electron-positron pairs. Now, if there's a magnetic field here, then the positrons will be directed upwards and then electrons will be directed downwards here because they have opposite charge and the Lorentz force has an opposite sign then. Now, what happens next? These electrons and positrons, they have very short mean free paths and they interact with the CMB and in particular, they upscatter CMB photons in inverse Compton scattering up to GeV photons, which we again should be able to observe. But what has been reported is a detection of TeV source, but without the GeV photons. And that means that there must have been a magnetic field between us and the blazar that was leading out these electron-positron pairs out of our line of sight. This is why we don't observe them. And this way, we had this, Neronov and Fovk were reporting this lower limit. There's a little bit of a debate around this observation, I have to say, for several reasons. So one reason is that what we could be seeing there could also just be pollution from magnetized galactic outflows. However, some groups are arguing that these outflows never be space filling enough to explain this non-detection of the GeV photons from blazars. Also, the sample is very limited, so there are not so many blazars around. It's really a cosmic coincidence that we have a blazar that really points directly into our line of sight. But this is something that is improving, has been improving during the last few years, I would say. And then the strongest other explanation for the non-detection of GeV emission from these blazars are certain plasma instabilities that would provide other ways to dissipate energy of the electron-positron pairs. And this is very, very hard to distinguish from a magnetic field along the line of sight, because we don't know the theory behind that very well, especially in that parameter regime of the intergalactic medium. But it's still the best constraint for primordial magnetic fields that has been suggested so far. There was another very exciting study released earlier this year, in fact. And that study is related to the Hubble tension, which I'm sure everybody has heard about. So if we observe the Hubble rate in the local universe by observing supernova explosions, for instance, we get values around 73, 74, maybe 75 kilometers per second per megaparsec. And that nowadays is significantly different from the value obtained from the CMB in the early universe. So error bars are shrinking, and nowadays we've reached a 5 sigma difference between these two observations. This is one of the biggest mysteries nowadays in cosmology, and there have been a lot of theoretical attempts to explain this, including very exotic types of models, like something like early dark energy, modified gravity, and so on. But earlier this year, it was proposed by Adamczyk and Pogosian that primordial magnetic fields could do the job as well. If you have a primordial magnetic field, that will enhance the density fluctuations in the early universe, which will in turn enhance the recombination rate. So you will have recombination occurring a little bit earlier than in the standard model, and that is enough to shift the obtained Hubble constant from the CMB to values that are closer to what we observe in the local universe. And I put here the typical field strength and correlation length that is needed in this parameter plot. So that might be the very first proof for the existence of a primordial magnetic field. Okay, let me compare this parameter plot that we have just looked at with magnetic fields that are observed in the local universe. I just scaled that, shrunk that down a little bit. This is the allowed parameter range for the void magnetic fields. And I put in now some observed magnetic fields, starting on small scales here on the Earth. We have a magnetic field, and the sun we have strong magnetic fields, or in stars in general. We see magnetic fields in the interstellar medium here on larger scales, where we can observe them directly with either synchrotron emission or with Faraday rotation measurements, or even sometimes with Zeeman splitting. We can see magnetic fields on galactic scales. Like this is one of my favorite observations of a galaxy showing M51 and the large scale magnetic field in that galaxy. In galaxies, we see magnetic field strength of something like 10 to the minus 5 Gauss, typically. And that is not too far away from magnetic fields that are observed in galaxy clusters. It's only like a factor of 10 below. And even there, we find sometimes synchrotron emission telling us that there are magnetic fields around. But all of these magnetic fields that we observe today in the universe, they most likely have no memory of their primordial origin. And I would like to spend 2 minutes on that topic. In dense regions of space, you can have efficient dynamo instabilities that amplify any magnetic seed field exponentially fast and with large growth rates. In particular, there's the small scale dynamo. This is something I've been working on during my PhD in Heidelberg. This is a process that converts turbulent kinetic energy into magnetic energy if there's a magnetic seed field. And I added here a small sketch showing how a magnetic flux rope can be stretched and twisted and folded if there's turbulent motions in the gas. And this happens again and again, and by this we can amplify the magnetic field exponentially fast. So there's a certain growth rate associated to that process, and this growth rate depends very much on the type of turbulence. So it increases with increasing Reynolds numbers. Now we have a theoretical background for this small-scale dynamo instability. In particular at ITA, we have applied small-scale dynamo theory to galaxy formation and plugged in typical numbers and found the evolution of magnetic fields in young galaxies. We find typical timescales of 1 or 10 mega years, depending on how you drive turbulence in these galaxies. There's also a lot of evidence from direct numerical simulations. So I'm showing here one example of a turbulent box. So a box where there's a weak seed field, turbulence is driven in this simulation, and then you can see that the magnetic field increases exponentially fast if you observe that here. And nowadays, even in cosmological simulations, you can see the small-scale dynamo operating. So if you have MHD, magnetohydrodynamics, in the cosmological code, for instance, in Ramses, you have it, you also have it in ARIPO, then you can see if you start with a weak seed field that the magnetic energy is exponentially growing. So since this kind of dynamo instability is very efficient in overdense cosmic regions, most likely you don't have any memory of the primordial magnetic field, and therefore we are really focusing on these cosmic voids. So let me talk about magnetogenesis in the early universe. So in principle, you can generate magnetic fields already during inflation or during the cosmological phase transitions. There are plenty of models around, therefore there are plenty of outcomes for the magnetic field strength. I don't go into detail here. But after these magnetic seed fields have been generated, they will evolve in the plasma. Since there's no more energy input, mostly we have to deal with decaying MHD turbulence. And that is described by the induction equation. So the evolution equation for the magnetic field, which is governed here by a term related to the velocity field, and a dissipation term that is determined by eta, so the magnetic resistivity. And very interesting consequence of the induction equation is that it implies that magnetic helicity is a conserved quantity. So magnetic helicity is A dot B, A being the vector potential, and you can calculate the magnetic field from the curl of the vector potential per definition. And magnetic helicity is a topological property of the magnetic field that is in MHD conserved in the limit of vanishing eta, vanishing magnetic resistivity. So if that term is much less than that one, magnetic helicity is conserved. And this has a very important consequence. So you can write magnetic helicity if you just replace this derivative by 1 over the correlation length. You can write A dot B as correlation length times B squared. And that implies if you don't have any energy input in the magnetic field, if the magnetic field just decays, the correlation length needs to increase. This is known as the inverse cascade, and it's very central if the magnetic field wants to survive until present day. There are some very detailed calculations on that, and also very advanced simulations showing how the magnetic field in decaying MHD turbulence evolves. I just show here one example where you start with a magnetic field generated during the electroweak phase transition. And if it's helical, it will evolve along this line and end up at a certain value that is given by recombination. Even for non-helical fields, you can transport the energy to larger scales, but not as efficiently. And things change very rapidly after a recombination. At recombination, the universe becomes neutral, and then the plasma and the properties become very different. And basically, in this work, we mostly assume that after recombination, the magnetic field is just frozen into the Hubble expansion. That only then changes with structure formation when MHD dynamos can occur and convert kinetic energy into magnetic energy until we end up with magnetic fields that we observe in galaxies today. So this part here is really suspect of very nonlinear structure formation. So anything that happens here is not related to the origin of the field. But if we observe magnetic fields in voids, this can open up a window into what happened in the very first seconds of the universe. So therefore, it's super interesting to describe that phase, that evolution of the magnetic field in the early universe in detail. And I will present you some new changes now that occur in the very beginning of that phase, in the very hot primordial plasma, where there can be a macroscopic quantum effect that leads to significant changes in this previously decaying MHD turbulence scenario. So yeah, some new twists from the chiral magnetic effect. So brief reminder, chirality describes the symmetry of an object. Like if they are achiral objects, and if you place them in front of a mirror, you can superimpose the two images. In physics, these are normal scalars like the particle density, the electric charge, or normal vectors like the velocity vector, the ohmic current, the electric field, also the vector potential. But there are also chiral objects, and the prime example for that are hands. If you place a hand in front of a mirror, you cannot superimpose the two pictures. And in physics, these are so-called pseudoscalars, for example, the magnetic charge, if it exists, or pseudo vectors or axial vectors. So any normal vector that you have that you take the curl of will be a pseudo vector, and you have to be very careful when you want to combine these different kinds of vectors. I will be talking for the next 15 minutes or so about this chiral density, which is also a pseudoscalar. So I am talking about the difference between the number density of left-handed particles and right-handed particles. Or I will often talk about the chiral chemical potential, which is related to that chiral particle density. So the difference between left and right-handed chemical potentials, which is a pseudoscalar. There's also an actual current associated to that. Now, if you have such a chiral chemical potential in the system, there are very exciting things that can happen. So we will be looking now at individual fermions here. So for instance, electrons, and they usually come with a momentum and a spin. So here you see a left-handed particle, and there are also right-handed particles where the spin is turning in the other direction. And we have many of these fermions in the early universe. And it's getting very interesting if you switch on a magnetic field in the early universe, because then the momenta of these fermions align, or the spins align to reach a minimum energy state. And it's extremely interesting if you have an asymmetry between the number of left and right-handed fermions. If you count here, we have one more right-handed fermion than left-handed fermion. And that means that there is an electric current in that case moving upwards in that picture, because you have more electrons going up than down. This is only relevant for very high energies. You need at least 10 MeV. Otherwise, any chiral asymmetry will very quickly vanish. But these temperatures are there in the early universe. And if you are at these very high energies, a chiral chemical potential, again, the difference between left and right-handed fermions, can lead to an additional electric current, which is given by this mu5 times B. This is the normal electric current, this is known as the chiral magnetic effect. This is really a standard model effect. It's very well known in high energy physics. It's no exotic physics. It's something that can even be observed in some experiments. So this effect is important at high energies, as I said, so in the very early universe. It is also potentially important in young neutron stars, because they also reach very high temperatures. And interestingly, you find the strongest magnetic fields in nature in so-called magnetars. So maybe there's a connection to the chiral magnetic effect. There are experiments showing evidence for this chiral magnetic effect. So heavy ion collisions, like here in Geneva at the LHC, for instance. And interestingly, there are also that this effect is very, very well known in condensed matter in some quantum materials, but I cannot talk about this today. Just want to highlight this is really a standard model effect that is very well known in particle physics. Let's see what happens if there's this additional current in the system. So I've talked about classical MHD, where you have an electric current given by the ohmic current. And if you combine this with Maxwell equations, you get the induction equation that I've shown before. And the induction equation tells you that magnetic helicity is a conserved quantity, which has very important consequences in the early universe. Now in chiral MHD, if you go to high temperatures, there's not only the ohmic current, there's also this chiral magnetic effect current. If you just have these two currents in the Maxwell equations, you can derive a chiral induction equation. So in comparison to what we've seen before, there's one additional term that is related to this chiral magnetic effect. Then in that case, you can also find a conservation law, but you'd see that not the magnetic helicity is conserved, but the magnetic helicity plus the chirality of the system. So there's this mu5 and there's an additional temperature dependent constant that is determined by the chiral magnetic effect. So the sum of these two are conserved, and that means you can, if you have an initial mu5 in the system, you can produce magnetic helicity. So what are the consequences of this new term? Therefore, I would like to briefly talk about how chiral MHD compares to classical mean field MHD that I think more of you are familiar with. So you all know the magnetic field has the sun has a large scale magnetic field like this. And we can understand where this magnetic field comes from again, looking at this induction equation. There's a dissipation term. If you only have this, the magnetic field will just decay. But there's also this induction term related to the velocity field. So if you have a large scale rotation, like if you have the sun like this and there's a magnetic field, the sun will rotate and it will wind up the magnetic field like that. This is the so-called omega dynamo. You have then generated out of a poloidal magnetic field, a toroidal field. So at some point, this mechanism will stop because there's no poloidal magnetic field left. So it's not the end of the story. So if you really want to understand where the solar magnetic field comes from, we can go to mean field theory that also takes into account the turbulent velocity field. So therefore, when one can split up the magnetic field into a mean field and the fluctuations, same for the velocity field. and then derive a mean field induction equation that you might have seen. So they are now, this is the evolution equation of the mean magnetic field, and there are now two new terms popping up. There's an additional contribution to the resistivity, and I like to compare that additional contribution to coffee. If you have a cup of coffee, and if you slowly put in some sugar, you only have molecular diffusion, and it will take roughly 30 days for the sugar to homogeneously distribute in your coffee. And then your coffee is cold, so it's not good to drink that. So what you do, you take a spoon and you stir it, and you induce turbulence in the system, and then within a second, your sugar is distributed and you can enjoy your coffee. So even in a small cup of coffee, turbulence really makes a big difference. In the universe, even more. And then there's this additional alpha term, which is also a transport coefficient that depends on the properties of turbulence, of the fluctuations in the field. And this alpha term can be shown to generate out of a toroidal field due to small twists of the magnetic field, a large scale colloidal field. So this really closes the loop. You can have an omega dynamo and then an alpha dynamo, and therefore generate a large scale magnetic field in the sun. This mean field induction equation now looks very similar formally to the chiral induction equation. So this is now the total chiral induction equation, not a mean field equation, but you can see by comparing this alpha dynamo term to this new mu5 term coming from this chiral magnetic effect, that this will lead to instability in the system and can amplify the magnetic field. This has been realized already a long time ago. I think I will briefly show you the full set of equations here that need to be solved. So there's this chiral induction equation, but of course it depends on the velocity field. So we also have to solve the Navier-Stokes equation. There's an evolution equation for the density, and there's of course also an evolution equation for the chiral chemical potential and for the chemical potential itself as well. So it's a very complicated system of equations. This is why I mostly rely on numerical simulations to solve these equations. And I'm using for this the pencil code. This is a grid-based code with very high order finite difference methods in space, and also high order time stepping methods. So this is a very well-known code for modeling MHD turbulence in different situations. And I have added these chiral contributions, these chiral terms in the code. So I'm setting up large 3D boxes with periodic boundary conditions with higher resolution. And I'm just interested in the evolution of these equations for different initial conditions. This is just a slice of my simulation that you also see in my background. Let's briefly look into some results. So there are many new effects in chiral MHD if you compare it to classical MHD. So first of all, we were interested in situations where we just start with a weak magnetic seed field, which in classical MHD, which I'm showing here, would be just decaying, because if we don't see a turbulence in the simulation, if we don't inject any kind of energy, it will just decay. But as soon as we switch on an initially large chiral asymmetry, which is here indicated by this mu5, we can see that the magnetic field grows exponentially until we reach some saturation value, which is defined by the conserved quantity in the system. This is the case if there's no strong turbulence in the system. If there is turbulence in the system, if there's only very small value of magnetic resistivity, then we see a very different evolution. Initially it's similar, but then turbulence is driven and the magnetic field evolves with a different growth rate. Just some snapshots here at different times. This is the magnetic field in the beginning that we typically set in here. Then there's during the initial dynamo amplification, we see a small scale instability. And later we see a large scale magnetic field building up. So there are very distinct phases, and turbulence plays a very important role here. I'm just looking at the time, and I think I'm very, very slow, so I will skip some of these results that I have prepared here. I mean, there are also strong effects, for instance, on the propagation of waves, but I'm running out of time, so I want to use my last 5 minutes, if I may, and showing you some physical results of this particular dynamo scenario in the early universe. So the question is, under which conditions can a chiral dynamo, such a dynamo instability that we have just seen in our simulation box, produce magnetic fields that are consistent with the observational constraints that I've spent so much time on explaining in the beginning? The problem is we don't know the initial conditions. There are a lot of models around for inflation, for the phase transitions, and so on, that produce a large variety of different initial magnetic fields and different initial chiral asymmetries in the system. So we are just looking at a very simple setup right now, considering a large initial chiral asymmetry and a weak seed field, weak magnetic seed field, and we will see what happens. So in the end, everything is determined by this conservation law that is valid for chiral MHD. So the sum of magnetic helicity and chirality is conserved. So if we just rewrite that, the final state, so the final sum should be the same as the initial value of that sum. And we are now interested in a case where we start with a vanishing magnetic helicity, but a large initial mu5, and we want to convert all of that into magnetic helicity at the final state, and the mu5 should vanish by then. Now we can go to the particle physicists and ask them what's the typical value of mu5, and they tell us if it is thermally produced, it will have a certain value. I will go through that very briefly. So similarly, we know from this quantum effect how this constant should be calculated, and we can just plug in typical numbers of the early universe, and we find a certain number for the magnetic helicity. Now remember, magnetic helicity can be written as the magnetic field strength squared times the correlation length of the magnetic field. And I don't want to remember you remembering any of these numbers. I want to show it in that parameter plot that we have discussed all the time. So I need to extend that a little bit to the right, because if you have a large chiral asymmetry, the chiral dynamo will operate on very small spatial scales. And there are two different phases of the dynamo, a phase where there's no turbulence and a late phase where there's like a highly nonlinear evolution, because the magnetic field that is generated drives turbulence. And this final point is basically given by the conservation law that I've just shown you. And once you have generated this strong magnetic field and then the temperature reduces, there will be no chiral effects anymore, and you will again just have decaying MHD turbulence, for which we know how it evolves in that parameter plot. And finally, we end up at a certain position in that parameter plot. If we use this thermally produced chiral asymmetry as an initial condition, we do not end up in the allowed parameter range allowed by these blazar observations. So this tells us something about the early universe. So we have certain possibilities to create stronger magnetic fields. So one way would be a non-thermal production of a chiral asymmetry. So there could be a decay of some long-lived particles, or you can include more than one fermion species. And this way you could shift the entire curve upwards. There could also be a different driving of turbulence, and that would result in a mean field chiral dynamo operating on larger scales, or there could be relevance of some viscous damping scale in chiral MHD. Both of these effects would shift the entire curve to the right, which would then match the observed constraints. or there might be also something wrong with these constraints that could be also an indication. For instance, there are there's a study of Caprini and Gabici showing that if you take into account a certain magnetic energy spectrum when you analyze these blazar observations, that there will be not a very strong increase towards larger scales of that lower limit. But we are also really not at the end of the story. There are more chiral anomalies in the early universe. There's a chiral vortical effect and a chiral separation effect, and all of these effects can also change the evolution of the primordial magnetic field. So there's really much more work to be done. And as usual, I mean, there can also be some beyond the standard model physics going on. So therefore, it's really important to constrain our observational knowledge of primordial magnetic fields more. And there are great possibilities in the next 10 years, 20 years to do that. There's CTA coming up, the Cherenkov telescope array, which will be very important for increasing our lower limits from these blazar observations. Of course, there's SKA, which we are all looking forward to. SKA is the magnetic field machine. It will collect so much more information about the local magnetic field in our universe, which will be very amazing for that kind of work. And also, we are looking forward to LISA, the space-based gravitational waves observatory, which might give us, or hopefully will give us, additional insight in gravitational waves from the early universe. And in fact, gravitational waves in the early universe can be coupled strongly with the primordial magnetic field. And there are some simulations of that showing that LISA will be able to observe magnetic fields for typical MHD scenarios in the early universe. Okay, I come to my conclusion. I hope I could show you that magnetic fields have been present during possibly the entire lifetime of the universe. It would be strange if there were no magnetic fields in this highly ionized primordial plasma. But their strength and their impact on cosmology are still very much an open question. For instance, we only recently found out about this chiral magnetic effect and how primordial magnetic fields are coupled to this chiral asymmetry, causing entirely new currents in the system. I've been studying this chiral MHD mostly with numerical simulations, and we are finding that there are very different instabilities in a chiral plasma in comparison to what we know from classical MHD. So we are hoping that with future observations of cosmic magnetic fields, we will be able to open up a window into the early universe and thereby be able to probe some of the very fundamental physics going on there. If you're interested in some of the details, please check out our papers. I listed some papers relevant for this talk here, and I'm happy to take some questions now.
Thank you very much, Jennifer. That's truly fascinating. Thank you. I am sure there are questions. I would like to ask people who would like to ask a question to raise their hands using the feature here in Zoom. And while people are looking for that button, it's in the chat window. But while we're waiting for the first hands to be raised, I have a question myself, which is undoubtedly going to be pretty naive. I apologize, but you showed at some point that the presence of a primordial or an early magnetic field affects the galaxy luminosity function, especially in the dwarf regime. And that sounds very similar to what some of the alternative dark matter models have been doing, right? If you sort of look at warm dark matter and so on, you change the luminosity function too. So how would you distinguish these effects? Is the imprint quantitatively sufficiently different that you can actually do non-degenerate science with that?
Well, this imprint of the primordial magnetic field on the primordial matter power spectrum highly depends on the strength of the magnetic field and also on the shape of the magnetic power spectrum. So you have a large freedom of what kind of imprints you can check there. I'm not very very much an expert of this dark matter imprints, but maybe they are more confined to a certain characteristic bump of the matter power spectrum, which might be possible to distinguish from at least some of the magnetic field scenarios. But I'm really not an expert on that, unfortunately.
Okay, well, more than I am, so thank you. Kees, you had your hand up next.
Yeah, very nice talk, Jennifer. There's one thing that a very naive question, because I just don't understand it. So maybe you could explain me a little bit once more why you expect a current, in which direction the current is then moving if you have this chiral effect. It's just something that
yes,
I missed.
Let me just go back to this picture. It was a little bit fast. I have to apologize. So the current depends on whether you have more left-handed or right-handed fermions in the system. So if you just look at this picture, in that case, so you have some left-handed fermions, and their spins align with the magnetic field, so that the momentum goes downwards in that case, while the momentum of the right-handed fermions goes upwards. Now, in that particular scenario, you have one more right-handed fermion in the system than left-handed, so you will have one more fermion moving upwards than downwards, and in that case, the current goes upwards. If
so
you
the
would,
blue arrows are the movements.
Yes, the momentum. Yes.
Ah, okay.
Yes.
I thought that was the spin direction.
No, that's the momentum. Yes.
Okay.
And then it was very clear, I think.
Then it becomes clear. Yes. Yeah. Okay. Thanks.
Good. Ralph.
So thanks. This was a very nice talk, very nice overview. I have a question about the potential other way to constrain the primordial field and its strength. And that concerns something that is very dear to my heart. It is the very first stars. And so I was wondering whether there are any news on magnetic fields in first star formation, and whether one could, for instance, look at the mass spectrum of the first stars as you may be able to constrain by galactic archaeology. So extremely indirectly, but anyway, there will be some constraints possible very soon. Whether you can use that to learn something about the very first seed fields that then are dynamo amplified, whether there are recent results on that.
Mm-hmm. So in general, this is something that is very difficult, I think, because the magnetic fields generated by all primordial mechanisms known are very weak. So we are talking about field strength of something like 10 to the minus 20 Gauss, or something like that. And even if you have this 10 to the minus 20 Gauss at the formation of the first stars, and you quickly will drive turbulence, and you will have these small scale dynamo instabilities that will amplify the field from 10 to the minus 20 Gauss up to 10 to the minus 6 or 10 to the minus 5 Gauss. So there are really many orders of magnitude in between. I'm not very confident that we can learn really about the primordial magnetic field strength. I think what might be more interesting are these indirect ways of effects on the primordial matter power spectrum that might affect then the formation of the first stars as well. So that might be something that can trace the primordial magnetic field in a better way. But mostly we are able to get only upper limits on the magnetic field by looking at dwarf galaxy simulations, which are typically in the mass regime that can be probed by realistic primordial magnetic field strength.
Okay, thanks.
So.
Okay, next question is by Uli.
Sorry, I forgot to unmute. Those chiral particles, what are they? I think I know that neutrinos are chiral by nature, but an electron can be either right-handed or left-handed. Is that correct?
Yes, I mean, you need a charged particle with a spin.
Yeah.
For this effect to happen. Otherwise, I mean, your particles might, the spin might still align with the magnetic field, but there's no additional current. So you need charged fermions for this effect. And one possibility is just looking at electrons, but there are several fermion species in the early universe.
And the electron, is it by nature right-handed or left-handed, or can it be both?
Well, for an electron, well, it depends on the spin in the early universe. So yeah, you just need some kind of fermion, and then the spin will align with the magnetic field. Interestingly, there's also a similar phenomenon in condensed matter in semi-metals, where you can actually treat holes in quantum materials as fermions with spin, as pseudoparticles. And it's interesting because in these conditions, these pseudoparticles are massless. So that's another very important criterion. The mass needs to be neglectable. If the temperature is too low, and for the early universe, the temperature, if the temperature drops below 10 MeV, then the mass of the fermions suddenly plays a role, and then the spin can flip. But at very high energies, the spin flip is suppressed very strongly. So this is where these kind of numbers come from. But once the temperature drops, if you have a chiral asymmetry, spins can flip, and this asymmetry will vanish quickly. But in this while semi-metals, that's not the case, because these particles are massless by definition. So you can have this effect there.
Okay, so what you are saying is that if the temperature is sufficiently high, then the electron gets a chiral nature, like the neutrino has now.
Yes, because the neutrino is almost massless. So
and the positron would have the opposite chirality. So this asymmetry that you are talking about, is it the meta-antimatter asymmetry in a way at high temperature?
Well, this is something that actually might be connected to meta-antimatter symmetry in the early universe. So, I mean, for this meta-antimatter symmetry, you somehow need to break the CP asymmetry in a way, and in a similar way, you can generate helical magnetic fields. They often go along with each other, and some of these baryogenesis models, they actually predict the generation of also a helical magnetic field. So this is something extremely exciting to study in terms of baryogenesis.
Okay, thank you.
But I'm not a particle physicist by nature, so I don't know.
I got a feeling where it could come from now. I was just wondering, where should this chirality come from? Okay, thank you.
So wonderful. While we see if there are any further questions, I actually have another question, which is related to the blazars, because at the end you showed, okay, it might be that there is some way of actually increasing the primordial magnetic field strength beyond what is naively expected, or maybe this lower limit from the blazars might be a little bit overestimated.
Yes.
So I think that's an interesting idea. Can you maybe give a little bit more thoughts on how or why that might be overestimated? And specifically, I could imagine that in the close proximity to blazars, there are pretty strong magnetic fields. How do you disentangle any effects from those magnetic fields from any void-based magnetic effects that you would get along the line of strength? That seems challenging to me, and that could contaminate this, I would expect.
Okay, of course, these jets from the blazars, they themselves are also magnetized. However, this typical mean-free path of the TeV photons that are emitted are a few tenth or even 100 megaparsecs. So they are not affected, or this positron electron pair generation happens very far outside from these jets. So this is something that is pretty safe, but in this analysis, there's also a great deal of modeling of the original blazar spectrum involved. So there's an idea of the initial TeV spectrum and of the energy cascade of this inverse Compton scattering of these positron electron pairs. So there is a certain amount of modeling involved there. It's not straightforward, and also there are only a couple of blazars around. So the original paper, I think, includes 5 blazars. Yeah, it's work in progress. There are more blazars or more analysis is coming in, and we hope with CTA that there will be a large improvement in terms of statistics. But you are absolutely right. It's not straightforward to do that. But for me, the biggest challenge for interpretation of these observations in terms of the magnetic field along the line of sight is actually that there might be other plasma instabilities. So there's the plasma beam instability during which electrons and positrons can also lose their energy, but that is something that depends very strongly on the density along the line of sight, which we don't know very well. So depending on the density, you might as well explain the non-detection of GeV photons by these other plasma instabilities. But there are different groups of people, and there has been a discussion for the last maybe 10 years, but there's no real conclusion about that yet.
All clear. Thank you.
Yeah.
Thank you very much. So I'll give one last call if there are any questions. Before, I'd like to go to 2 logistical announcements. So I see no hands. So yeah, before we thank Jennifer again for an amazing talk, I would like to make 2 announcements. Normally, of course, when we have speakers visiting Heidelberg, there are opportunities to meet with the speaker for a one-on-one conversation. Now that we're online, I would like to let everybody know that if you would like to speak with Jennifer at some point, I don't know, during the next week or so, you're welcome to either contact her directly. I see your Zoom name is actually your email address, so that's very straightforward. Or otherwise, feel free to email me, and then I'll put you in touch to have a conversation. Other than that, I should also announce next week's Joint Astronomy Colloquium, and to do that, I will steal the screen sharing briefly. Sorry. And show the announcement for next week. So next week we'll have Paola Caselli speaking from MPE, who will actually take us from the very large scales that we just saw to the very smallest ones, and she'll be talking about our own astrochemical origins. So that is next week. I look forward to seeing everybody then. And before we go, I would like to ask everybody to kindly unmute again and give Jennifer a very warm thank you in applause. Thank you.